Moving on to problem number 11. Use the given information to find the number of degrees of freedom, the critical values chi squared sub L and chi squared sub R, and the confidence interval estimate of sigma. Is it reasonable to assume that a simple random sample has been selected from a population with a normal distribution? Alright, so here is the confidence level, 80%. Here's our n equals 29, and here's our s equals 0.26. And so we'll need all of this in order to get all these answers. Alright, so this is chi-square distribution. How do you know it's a chi-square distribution? Well, we are dealing with population standard deviation or population variance. That also uses the chi-square values. Now, just like with the t distribution, we have degrees of freedom, and the degrees of freedom are n minus 1. So if n is 29, your degrees of freedom is going to be 28. You just subtract 1 from n. Okay. Now, finding these critical values is a little tricky. The reason why we have a right and a left critical value with chi-square, we didn't have that with a z distribution. We didn't have that with the t distribution. Chi-square's values, if put under a bell curve, are generally not symmetric. I mean, they may be skewed one way or the other. And so, since they are skewed, I'm not going to have the same value, I guess, on the, if you think about this like an x-axis, this is where my critical values would be. I'm not going to have the same positive and negative value that will correspond to a similar area or the same area, because we still want the same area on both sides, just like with the z distribution or the t distribution. This problem that we're working said that we wanted an 80% confidence interval or confidence level. So that means that alpha is equal to 1 minus 0.8, which is 0.2. So this is the total area that I'll have in my two critical regions. Okay? So if this is the total area from two regions, then I'm going to have the same area on each side, but since the items are skewed one way, that's going to mean that I'm going to have different critical values on the left side and on the right side. So if that total area in my critical region is 0.2, I say 0.2 divided by 2, and I get 0.1. Alright, the other problem, and so that's an area 0.1 and that's an area 0.1. The other problem that we run into sometimes is the chi-square distribution chart. If you really understand what's going on right now, the chi distribution chart is not cumulative from left to right like the z-score chart is. Okay, now let's look at that chart real quick. I'm just going to go to your textbook. It's right after the t distribution chart. We have a chi-square chart. Notice up here it says area to the right of the critical value. That's not really what we're used to with the z-score chart. We had areas that were cumulative from left to right. These areas that we're given are the area to the right of the critical value. Very important. Area to the right of the critical value. So what does that mean? That means that if I want to know the critical number, this is going to be on the right side. So this is my chi squared sub R. If I want to know this critical value, the area to the right of that is 0.1. So I want to look in the column for 0.1. That will give me my chi squared sub R. Alright, if I want to find this value right here, that's my chi squared sub L, it's my left critical value, then what will the area to the right of this be? So if I have 0.1 here, the area to the right of that is going to be 0.9. So I have to look in the column for 0.9 to give me my left critical value. Again, that's because this table shows the area to the right of the critical value. Okay. Our degrees of freedom matters. We found on this problem that our degrees of freedom was 28. Okay, so we're down here at 28. I need to see which column. Look at the column heading here. All right, point 1. This is for my right chi-square critical value. Now go down to 28. So it's this column, and let's go down to 28. So 28 here, right here. All right, this is 28. Go across to the correct column. This was the column for point 1. So my chi-square sub r is 37.916. So this right here, 37.916. My left chi-square critical value, I need the column for 0.9, so that's this one right here. It's just one over to the left, actually. All right, so go to 28. So my chi-square sub L, or my left chi-square critical value, is 18.939. This is 18.939. All right, so if we look at our answers so far, so there's your chi-square sub L. They actually wanted that one first. And then there's your chi-square sub R. So these are the critical values there. Now, the confidence interval estimate. So this is where we're doing our actual confidence interval. So we need a formula to find the confidence interval. All right, so I'm going to go back to your textbook, and let's go into that section. It's chapter 7, section 4, I believe. Yeah, estimating a population standard deviation or variance. That's chi-square. Okay. And so the way that we find the interval, and since we're doing this right here is for sigma squared, so this is the variance if we wanted the variance. This one right here has a sigma squared here, but that doesn't need to be there. That 2 doesn't. That's a typo. So if your textbook has the 2, then just imagine that it's not there, because see what they did from the variance. They just took the square root of both sides. They took the square root of the right side, the square root of the middle, and the square root of the left side, and that gives us this formula, except for this needs to be just sigma. Okay, so this is what we have to figure out. We have to do the square root of n minus 1 times s squared, that's the variance or the standard sample standard deviation squared, over chi squared sub r, and then we do the same thing here except we have it over chi squared sub L. Okay, so those are the 2 calculations that we need to do. So n minus 1 times s squared over chi squared sub r. That's our left endpoint of our confidence interval. All right, and it should, since it's the left endpoint, you know, it should be the smaller number when we get it. You'll see that it is. So we have to use this right here, the right critical value. And so this is going to equal, when we plug all that stuff in, n minus 1, n was 29 on this problem, so that's 28 times, let's see if the problem gave us, it had to have given us, there, s equals 0.26. If that's not given and you have a data set, then you just have to find it. All right, but s is 0.26. I'm going to write that down. S equals 0.26. So this is 0.26 squared over, your right critical value is 37.916. All right, so this is going to give us the left endpoint of our confidence interval. All right, so I'll just pull up the calculator. I would probably say 0.26 squared first, and then say that times 28 divided by 37.916. And once you do that, then take the square root. All right. If we used one more decimal than is used with the original data set, I guess we'd have to know what the original data items were. I'm going to say that probably 2 or 3 places would be fine here. Since I was given a standard deviation, a sample standard deviation with 2 decimal places, I'm thinking 2 decimal places is probably the best, but let's look back at the problem. It probably tells us what to round. Round to 2 decimal places. Okay. So if you look at our calculator, 2 decimal places, that's going to be 0.22. It's going to be the smaller or the left endpoint of the interval. Now we need to figure out this one, the right endpoint. It's kind of weird because for the left endpoint, you use the right critical number, and for the right endpoint, you're going to use the left critical number. So our other formula is the same as this formula, except we have the left critical number. All right, so that's the square root of 28 times 0.26 squared, I mean all that's the same, over our left critical value. That's 18.939. Okay, so 28 times 0.26 squared, so I'm just going to say times 0.26 times 0.26, and then say divided by 18.939, and then I'm going to take the square root of that. All right, and if I round this to 2 places, that's 0.32. So my right endpoint here, 0.32. All right, move on to question 12. The same thing on this problem. It looks like we have a different confidence level. So that was 11. Here's 12. I noticed we had a 99% confidence level. So alpha, or our total area of our critical regions, is going to equal 1 minus 0.99, all right, or 0.01. So this is the total area for both of the critical regions together. So the area for one of the critical regions is going to be 0.01 divided by 2. All right. And so that's 0.005. So that means when we have, we have this, it's not going to be bell-shaped. It's going to be skewed left or to the right probably. But the area on each end in our critical region is going to be 0.005. And so the way that we use that, remember in our chi-square distribution table, that if we want to know what critical number we have here for the right critical number, that's chi-squared sub r, then we need to use the area to the right of that, which is 0.005. All right, and then to find the critical number right here, that's chi-squared sub L, I need to use, or I need to go to my chi-square distribution chart, critical value chart, and I'm going to have to use an area of whatever's to the right here. So it's 1 minus 0.005, or 0.995. All right. So those are the 2 values that I'll use in my table to get my right critical number and my left critical number. So let's look at the table. Again, the table is right after the z-score chart in the back, or I'm sorry, right after the t-distribution and z-score charts in the back. All right. Now, we need to know how many data items we had. I didn't identify that. We have n equals 26. So since n is 26, and I'll go ahead and write that down, then that means our degrees of freedom is 26 minus 1, or 25. So we use that in our table. So I need to go to 25. Now first, let me figure out which column I need to be in. All right, my right critical value, I said we needed an area of 0.005 to the right. So if I go down to 25, then you can see my right critical value is going to be 46.928. So this value right here is going to be 46.928. Now I need to look for an area of 0.995 to the right. So let's see which column that is, 0.995 to the right, go down to 25. So my left critical value is going to be 10.520. Alright, so there are my two critical values. And we can double check those real quick. See, 10.520 was the left critical value. The right critical value was 46.928. Now, to construct the confidence interval estimate, we need our formula for the left endpoint and for the right endpoint of my interval. So you can do either one, it doesn't matter. For both of those, I do need my standard deviation is 65.6 here. My standard deviation is 65.6. Alright, so my left critical endpoint, that's going to be the square root, or I have to use to find my left confidence endpoint. I use my left critical value. It's going to be the square root of n minus 1. So n minus 1 is 26 minus 1 is 25 times the standard deviation squared over, now if I want the left endpoint, I have to use the right critical number. So it's 46.928. And this is going to give me the left endpoint of my confidence interval. I'm going to go ahead and write down what I need for my right endpoint of my confidence interval. 25 times 65.6 squared over, since this is going to be the right endpoint of my confidence interval, I need the left critical value. That's 10.520. Okay? So let's do those in the calculator real quick. So I'm going to say 65.6 squared times 25 divided by 46.928, and then I take the square root of that. I'm going to again round this to 2 decimal places. Alright, so my left endpoint of my confidence interval, 47.88. My right endpoint of my confidence interval, I'm going to find next. All right, 65.6 squared times 25 divided by 10.520, and then I take the square root of that. So my right endpoint around the two places is 101.13. Okay, so here's my confidence interval. Let's go back and look. All right, so it appears that they rounded to one place, so that's the only thing different than mine. 47.9 is less than, sigma is less than 101.1. Okay, so there's the answer for number 12. Number 13, here's the confidence level of this problem. Here's x bar, so that is a mean, sample mean, and here is S, sample standard deviation. So that's $16,584. Okay. %, confidence interval, n equals 81, and S equals 16,584. So the next thing that we need to do is find the critical values. All right, so I need to find my left critical value and my right critical value. So let's see if we can do it this time without drawing a picture and maybe just visualize it. So since we have a 99% confidence level, that's going to give us an alpha of 1 minus 0.99 or 0.01. So if I say 0.01 divided by 2, that will give me the area of each critical region. The area of both critical regions is 0.01. There's two critical regions, one on the left and one on the right. So I have to divide it by 2, get 0.005. All right, so remember the table is going to give us the critical value where the area is 0.005 to the right if I use 0.005. Okay, so let's go to the table, and you can actually get the table from the problem if you just click this box here. You see it brings up a copy of the table, and you could print it out if you needed to. What was our degrees of freedom? We had 81 items, so 80 would be our degrees of freedom. And then we need the column 0.005. It is really small there. So if you don't have your video on high resolution, you might want to do that so that you can see all these small numbers, or just go to your, go to your sheet and go to where degrees of freedom is equal to 80 and the area to the right is 0.005. And this is going to give us our right critical value. So here's 80 right here, 116.321. That's our right critical value. Our left critical value is going to have an area to the right of 1 minus 0.005 or 0.995. All right, so let's go back to our table. And we need to make sure we are in the 0.995 column. That's this first column here. Go down to degrees of freedom 80. And that is a critical value of 51.172. All right. So now I'm almost ready to construct my confidence interval. Remember, with the confidence interval, you need to use the right critical number for the left endpoint and the left critical number for the right endpoint. So I'm going to find the square root of n minus 1, which was 80, times s squared. S was 16,584, over, since this is the left, I use the right. So over 116.321. All right, that's going to be my left endpoint of my confidence interval. My right endpoint is going to be same n, 80, times 16,584 squared, over, all right, so this is my right endpoint, so I need to use my left critical value. That's 51.172. All right, so now I'm going to use my calculator to see what these are. So 16,584 squared, wow, that's a big number, times 80, that's even bigger, divided by 116.321, and then don't forget to take the square root of that. All right, so I believe this was money, so what I'm going to do is I'm going to make sure I round the two places here, and then I can always go back and round to 1 if I have to. So 13,753, and if I round to two places, that'll be 0.25. Okay, so now let's calculate the right endpoint of my confidence interval. That's going to be 16,584 squared times 80 divided by 51.172, and then take the square root of that. So I've got 20,735, and if I round to two places, it's 0.67. Okay, so let's check our answer here. All right, they rounded to the nearest dollar, so that's where mine will be a little different. 13,753 if you round to the nearest dollar, and then 20,700, and if you round to the nearest dollar, that becomes 736. Okay. All right, so that's the interval on number 13. All right, let's go to problem 14. Okay. A simple random sample from a population with a normal distribution of 97 body temperatures has a mean of 98.7 degrees Fahrenheit and a standard deviation of 0.69 degrees Fahrenheit. Construct a 90% confidence interval estimate of the standard deviation of body temperature of all healthy humans. Okay. So just like with the last problem, I don't think I pointed out, but with the last problem, they gave us the mean, but we didn't really use the mean. So it looks like we have a mean here, right there. Probably not going to use this either. We have a 90% confidence interval estimate, so 90% is going to correspond to, we say 1 minus 0.9 or 0.1. That's the total area of the critical regions. Divide that by 2 and you get 0.05. All right, so this is the area of the critical regions. So I need to use this to get the right critical number. And then to get the left critical number, I'll say 1 minus this. I want to use 0.95 in my table to get the left critical value. All right, so let's figure out the degrees of freedom real quick. Our N, 97. So we're probably going to have to get as close to 97 as possible. So this may give us a little bit of an error whenever we do it, depending on what kind of table we use. All right, so that was 97. So if N equals 97, our degrees of freedom is going to be 97 minus 1, or 96. And let's look at the table. The table goes 80, 90, 100. So 96, the closest thing to 96 we have is 100. Just know that our answer is not going to be just spot on because of that. All right, so it seems like we could maybe find what we need if we had a little bit, if it was just a little bit more precise, but that's okay. All right, so we have a standard deviation of 0.69. So our standard deviation, well, S, equals 0.69. I believe we could probably use that mean and the z-score chart to get a closer estimate of what I actually need for my critical values. So I'm going to work this out just like a normal chi-square, and then if we have to do that on this type of problem, then I'll come back and I'll show you how to do that. All right, but let's find what we need. We're going to have to use 100 because that's the closest thing we have to 96. So that's, again, that's not very good because we're estimating here now, big time. The area to the right, we said for a 99% confidence interval was 0.01, so we have to use 0.005. All right, so no, it was actually 90%, so 0.1, so we're going to use 0.05. Let's go to this one here. 0.05 is this column, so go down to 100. That's 124.342. So that was right, 124.342. For the left, we need to use the column that has 0.95. So I went up a little too far. 0.95 is going to be over here, right there. Go down to 100. 77.929. And again, I know these critical values aren't even close. Well, they're close to what I should use, but they're not real close to what I should use. And that's because our table doesn't have 96 degrees of freedom. It goes from 90 to 100, so I used 100. So these are actually just going to be estimated answers. Even though all this stuff is estimated, this is going to be, I guess, doubly estimated. All right, so we need to find the left and the right endpoints. So I need n minus 1, which is 96, times standard deviation squared over, if it's the left endpoint, I use the right critical number. Alright, I'm going to do the same thing here. It's the same numerator. It's the right endpoint, so I use the left critical number. I want to know just how far off we actually are going to be to the answers we should get. This should be interesting. Alright, so I want to work this out. So I'm going to say 0.69 squared times 96 equals alright, and then divide that by 124.342. And now take the square root of that. So if I go to 2 decimal places, that's 0.61. Alright, so that's the left that I got. Now let's see what I get for the right endpoint. Let's see, 0.69 squared times 96 divided by 77.929. And then we take the square root of that. So if I go to 2 decimal places, that'll be 0.77. Again, I know this is off. Why do I know it's off? Because of the degrees of freedom that we had to use, and then what our table gave us. We really had no option if we wanted to just use the chi-square distribution. All right. So let's see how far we are off. We're not off by much, actually. We got 0.61 for the left, 0.77 for the right. So if you look, when you hover over, look at the correct answers it takes. And I guess it's taking these answers because even though we don't have a table that shows us 97 degrees or 96 degrees of freedom, the answers that it takes 0.77 plus or minus 0.2, 0.78 plus or minus 0.2, 0.81 plus or minus 0.2, so or 0.02. So it's taken a lot of different answers because of that error that we could have gotten. So if you would put if I would have put 0.78 here, 0.79, 0.80, 0.81, it would take all those answers. So didn't actually have to redo it, but you know, it wouldn't hurt if I had a table that showed that. Then those degrees of freedom, then I could go back and do that. But with what we have, I think we did a pretty good job. Is it safe to conclude that the population standard deviation is less than 1.6? So here's what it says it's less than, or the population standard deviation, 90% confidence interval that the actual would fall in this. 0.61 and 0.77. 1.6 is way off of that. So is it safe to conclude that the population standard deviation is less than this? Yes, it would be. This is out of that interval, and I would say yes. It says the conclusion is safe because 1.60 is out of the confidence interval, and because it's also a lot more than what we actually got, and we're looking for it. Would it be okay to assume that it's less than this? If it would have said more, the answer would be no. Since it said less, yes. All right, so let's move on to problem 15. Now, I usually have a couple questions a semester on a problem like this out of the textbook or on the test, or on the homework even, because students a lot of times, for some reason, get away from using their book. They've been able to figure out how to work some of these problems without using their book at all, and then they come down to a question like this, and on the homework it may not give you this table, and so they're like, what table are you talking about? That's what I've gotten in the past. But on this problem, the table was provided, so you'll see just how easy this really is. Assume that the sample is a simple random sample obtained from a normally distributed population of IQ scores of statistics professors. Use the table to find the minimum sample size needed to be 95% confident that the sample standard deviation S is within 40% of the population standard deviation. Is this sample size practical? Well, first off, practical sample sizes would be ones that are small. You're not going to be able to have thousands in your study if you ever are able to do a study unless you work for a really big company and have a lot of finances, a lot of backing. So we want to be 95% confident. In this table, there's a top part and a bottom part. 95% confident is the top, 99% confident is the bottom. Then we want to be within 40%. So go down here to 40%, and this tells you how big N, the smallest value of N, 12. 40%, 95% confident, 12. The minimum sample size needed is 12. Is this practical? 12 is a pretty small sample size. So yes, the sample size is small enough to be practical for most applications. I'd be willing to bet that if you tried hard enough, if you wanted to maybe conduct a small survey or a small study, if 12 of your friends use Twitter, you could figure out 12 people to call. That's pretty convenient to have a small number like that. All right. Okay, this is transitioning over now into Chapter 8. Chapter 8 is on hypothesis testing. So with hypothesis testing, we have a lot of small parts that we have to put together. And the first part that you're tested on right here is the alternate and null hypothesis. If you haven't read this section, very important to read this section because it's hard enough to understand it if you have read the section. So make sure that you read it if you haven't. All right. So what we want to do, it says, here's our claim right here. The mean weight of a beauty pageant winners is 109 pounds. A study of 24 randomly selected beauty pageants resulted in a mean winner weight of 111 pounds. Express the original claim in symbolic form. So what is this thing claiming? It says the claim is the mean weight of beauty pageant winners is 109 pounds. Okay? Mean is mu. The claim is that mu is 109 pounds. So mu equals 109. That's the claim. Okay? Now, identify the null and alternate hypothesis. So here's how you find the null and alternate hypothesis. First, you write down the claim. All right? So we have mu equals 109. Then write down the opposite of the claim. So write down the opposite of equal to is not equal to. So mu is not equal to 109. Okay? The expression that you have written down that has equality, which is either going to be an equal to bar under a greater than or less than, or just an equal to, that expression is always your null hypothesis. And for a null hypothesis, we use H sub O. So for this claim, our null hypothesis is going to be mu equals 109. Our alternate hypothesis is H sub 1. That's going to be mu is not equal to 109. Null hypothesis, alternate hypothesis. Okay. So in this problem here, H sub O, mu equals 109. H sub 1, the alternate hypothesis, mu is not equal to 109. Okay, let's look at another one of those. I think we have a couple of those on here. So first, we want to express the original claim. Here's the claim. High school teachers have incomes with a standard deviation that is less than 22,250. So I heard standard deviation less than 22,250. Less than. Okay? So what is the opposite of less than? You may just be thinking greater than, but it's not going to be. The opposite is going to be greater than or equal to. So when we do the opposite of a less than inequality symbol, that's going to be greater than or equal to. So less than and greater than makes sense, but you also have to put the equal to on there. And I'll show you why in just a second. That's because now we look at the two. The one that has equality, that's going to be the equal to bar. We take it and we make it equals And that is now our null hypothesis H sub O. Again, here's what I did. I took the claim. You have to write down the original claim. You write the opposite of it. Put an equal to bar under your inequality if you have one. Then the one with equality, which is this one, you make that your null hypothesis by using the equals. Not the greater than, the equals. Now the other one, the one you didn't just use, that's the alternate hypothesis. And you still have to use whatever symbol is with it. Less than 22,250. All right, so look. Null hypothesis, 22,250. Alternate hypothesis, sigma is less than 22,250. The null hypothesis always has equality, always has equals. All right, here's another one. Here's the claim. At least 26% of internet users pay bills online. At least 26% of users. Now, percentage. So what is that percentage? That is a proportion. Okay? So 26%. It said at least 26%. So proportion is at least. That means greater than or equal to 0.26. At least 26% is greater than or equal to. So the opposite of that is just going to be less than. You don't put the equal to bar. It's just less than. Okay? Now, look at the two that you have written down. The one that has equality, that's going to be your null hypothesis. So that's going to be your H sub O. So H sub O. And then, we don't write down this. We have to write equals. So P equals 0.26. My alternate hypothesis is going to be the other one, written exactly like it is. P is less than 0.26. Okay? Null hypothesis equals alternate hypothesis on this particular one had less than. All right, make a decision about the given claim. Do not use any formal procedures and exact calculations. Only use the rare event rule. A coin favors heads when tossed. Now, this isn't talking about any coin. This is talking about just a random coin. And there are 15 heads and 18 tosses. Well, think about it. If you flipped a coin and for some reason it came up on heads 15 out of 18 times, using common sense, you would say, whoa, something is wrong with this coin. It's always coming up on heads. It's okay that it's coming up on heads. It's just there's something wrong with this coin. Maybe it's some kind of trick coin. All right, so would there be enough evidence here to support the claim that a coin favors heads when tossed? Yes. I mean, it's okay. There appears to be sufficient evidence to support that the claim, because there are substantially more heads than tails. All right? Not every coin, but just this particular coin. All right? 20. All right. Test statistic. So we need the formula for the test statistic of a proportion. All right, let's see. The claim is that the proportion of peas with yellow pods is equal to 0.25. The sample statistic from one experiment includes 520 peas with 148 of them having yellow pods. Find the value of the test statistic. All right, so we have an actual formula for a proportion test statistic. Every parameter, a proportion, a standard deviation, a mean, they all have different formulas. So this is for a proportion. I'm sure I could get the formula here and help me solve this or review an example, but let's go to your textbook real quick. All right, so we are in chapter 8. Again, if you're not reading your sections, this stuff is confusing enough with reading your sections, so please read them. All right, we need the formula for a proportion test statistic. It's in this first, or 8.2 somewhere. And I may have passed it. And I may not have. So let's just keep going. If we can't find it, we will eventually just view an example and see where they give it to us. All right, here it is here. You say, well, how do you know that's a proportion test statistic right away? Because I see P's and Q's and all that kind of fun stuff in there. All right, so this is our test statistic formula for a proportion. We have P hat, remember that's a point estimate, so that comes from the sample, minus P. P is the population proportion over the square root of P times Q divided by N. All right. So our test statistic is the square root of the square root's on the bottom. So P hat minus P, which is actually P hat minus P over the square root of P times Q over N. All right. P hat comes from the sample. This is a population proportion. And this P is like a success and a failure. N is the total number. All right. So let's see. See if I can pull this up right here. Sure can. This is problem number 20. All right, so here is the population proportion claim. The claim is that the proportion of P's with yellow pods is equal to 0.25. So P equals 0.25. The P hat, that's going to come from the actual sample here. The sample statistics from one experiment include 520 P's with 148 of them having yellow pods. So that's going to be 148 over 520, part over total. Alright, so I would keep that as close to that as possible. So I'm actually not even going to write down a decimal. I'm going to just type that in when I need it. Alright, so remember in the denominator of our test statistic, and this is our test statistic, this goes with our problem, we have P times Q divided by N. N, remember, is the total number. So our test statistic Z is going to be equal to 148 over 520 minus 0.25 over the square root of, what was P? 0.25 times Q, 0.75 divided by N. N was 520. So here's what we need to do. So what I'm going to do is I'm going to work out the top, and then I'm going to write down a really long decimal. Let's see what I get. So 148 divided by 520 is this, minus 0.25. So that's my numerator. That's what I'm going to write down. And I know it's kind of a pain, but unless you store that in your calculator, you need to bring that out to several decimal places. So I'm just going to copy it down to about this many places. All right, over, now I have to calculate this. So 0.25 times 0.75 equals this, divided by 520, and then I have to take the square root of that. So you see that gives me a really long decimal as well, so I'm going to copy it down to several places. 0.018988863. So now I'm going to divide these. If you can keep them exact, that would be great, but carrying them out several places should provide enough margin for error not to give us the wrong answer. Divided by 0.018988863. Alright, so here's our test statistic. Since this is a z-score, we're going to round it to 2 places. So 1.82. That's what we need to type in, 1.82. Alright, so that's number 20.